Okay, let's continue, please, because I want to stop in time. And as I said, the most well-accepted way of dealing with uncertainty is probability theory. Who of you, just a show of hands, is familiar with the basic notion of probability? Okay, so that's in empirical research, the course that you learn it, or where is it? Where do you get the basis from? From which course? Statistics. What is it? Second year? No. Statistical methods. Okay, I thought it was called empirical methods. No, statistical method. Okay, good. So. And that's in principle compulsory for everybody. So that's good news, because then I tell you something that you should already know. And the main reason for repeating it here is to bring it up in the machine learning method that we're going to talk about on Monday. Sort of one of the sort of most simple ones, the Bayesian naive Bayes algorithms. I'm not sure whether it was discussed in the, my understanding from the course statistical method was that it was also lots about setting up experiments. There is a philosophical discussion about probability theory, and that is sort of what does it mean for something to, how do you interpret the probabilities that are given to an event. And there is a sort of two philosophies about it. There's objectivists and frequentists is the first one, where the probability of an event is really determined by the relative frequency of this event if you run a number of experiments to infinity. So that's the definition of really the frequency of how often does a certain event occurs. And the alternative is the subjective, the more Bayesian approach, where you have a degree of belief, which is not necessarily based on a statistical objective measurement of experiments. And it's not an essential part of this course, at least, but I think it is quite important to think about this in the first instance. So take as an example, for example, that let's look at the frequentists, and is the probability is only a property of repeated experiments. So it doesn't say anything about the individuals itself. So if you read in a newspaper, 1 in 5 people is having an affair, then there are two ways of looking at it. I could look at you and I could say, okay, the chances that you have an affair is 20%. That would be the assumption that might be based on the Bayesian view of things, a subjective way. So the frequentists would say, if I pick 1 of 5 people out here, 20% of the people here, they might have an affair, which doesn't say anything about the individuals, but says something about the distribution of the people in the room. So basically, the probability that Bob is having an affair is 1 in 5 is the wrong interpretation according to the frequentist interpretation of probabilities. Whereas the probability that a randomly chosen person is having an affair is 1 in 5. So it's a difference between saying, I believe that you might have an affair with 20% probability, as opposed to say, I take every 5th person out of this room and they will have an affair. It's two different ways of interpreting this, two different semantics to this, and I think it's quite an interesting, it's important to think about this. So in Bayesianism, so the subjective way of things is probability and expression of the uncertainty. So how uncertain am I about a certain fact to be true or false? So you have a certain dice and you assign a property to this dice of saying, okay, it's either a 1 or 2 or 3 or 4 or 5 or 6. And that the probability that one person in the room would have an affair would be 20%. And the difference is really that the frequentists has no idea whether Bob is having an affair or not. It's only, you repeat the experiments with the dice, you repeat the experiment with taking people out of this room and checking whether they have an affair or not, that you can make a statement about this statement as is supposed in the newspaper. So there are two different ways of thinking this. One is a property of the individual and one is the property of the experiment. And apparently, as I'm told, because I'm absolutely not an expert in this, this has quite some impact on the way that you deal with the mathematics, with the probabilities in general, and experiments, setting up your experiments. What they have in common is that they share the same mathematical foundation. And that is what I'm going to talk about in the next 20 minutes, maybe. So let's start from the intended meaning. And the intended meaning is that we have a sample space. And then basically we run an experiment, and the result of each of these experiments could be is defined in the sample space. So we have we throw a dice, and the chances is that the two things that my sample can have is that it lands on the head or it lands on the tail. If I throw a dice, it can be a 1, a 2, a 3, a 4, and a 5, and a 6. And if I threw two dice, then I have my result is pairs. So the first dice gets a 1, the second one gets a 1. Would be one possible outcome, so it's one element of my sample space. So basically the sample space is a set of the single outcomes of an experiment. And then based on the notion of the sample space, you can define some event space. So that's all the subsets of the sample space. So we have an event that 1 and 2, the two dice would happen. And basically it's the events that we can assign the probability to. So if the sample space is finite, the case that we always look into this simple introduction here, then the power set of the sample space is usually considered to be the event space. So all possible combinations of events from the sample. And then there has been, on the basis of this, there has been the famous Kolmogorov axioms that define the probability functions in a way that these are the constraints that a probability function must fulfill in order to work properly as a probability function. And there is an argument that any formalism that doesn't adhere to these axioms, these three axioms, can't be a proper probabilistic system, which I might or might not explain on Monday, I have to see. And basically the conditions that you have is that your probability that you assign to an event is between 0 and 1. So that's exactly the same as with the fuzzy sets theory, but with a completely different meaning, so don't confuse the two things. If you take the entire event space, then the probability is 1. So if I pick an experiment result outcome and I take the entire outcome, then I will get a result. And the last one is that if I have two events, then I can combine them, taking the probability of the first event plus the probability of the second event. And if they are dependent, I have to take off the intersection of the two, because otherwise it would be counted twice. So for independent events A and B, it is just the sum of the probabilities. And these are the three axioms that allow us to axiomatize many of the properties, so and also do some algebraic calculation on them. So one of the things you can that follows from the three axioms is that if you take the empty event space, if you take the empty event, so none of the options is chosen, then the probability of this is 0. And basically the idea is that you start with the axiom that the full event space has a probability of 1, which is the second axiom. You use simple set theory that the empty set and the full space are disjoint, so they're independent, so you can apply the third axiom, and then there is some more, you just bring the probability of the full sample event space to the other side, and that basically gets you the information that this one has to be 0, because it's -1, and this one has to be between 0 and 1, so it has to be 0. So that's a simple way of calculating with the axioms that we've just seen in order to derive new information about probabilities. Another one is that if A is a subset of B, then the probability of A is smaller than the probability of B. And you start out with a simple definition by set theory. So B is simply the same as A union B of A. So if A is a subset of B, then if you take A away from B and you add A again, then you get B. Yeah. So if that is B and you have A, then B is the same as A plus B minus A. It's just a sort of rewriting according to set theory. And then you apply the third axiom of the Kolmogorov axioms so that you get this information out of it. Yeah, because B is A plus something, and this something is between 0 and 1, so A must be smaller than B. So this is just an example of new facts about probabilities that you can derive from these three axioms in very straightforward ways. Okay, so this is sort of the events and sample space that we want our semantics on. And now the question is the language. Which kind of language do we use? And this is the language of prior and unconditional probabilities for propositions. So we have some propositional statement that the probability of a dice throw on a 6 is 1 out of 6. Or the probability of the weather being sunny, some value between 0 and 2. So that gives us a probabilistic proposition with which we can then build, do reasoning over and represent the knowledge that's available. Sometimes we abbreviate that if we have a Boolean statement that the probability of X being true just by the probability of X. And in the Bayesian interpretation of the statistics, this corresponds to the belief prior to the arrival of any new evidence. So this is the Bayesian way of introducing those. Then we can represent for a variable, we can represent the probabilities as a probability distribution. So we just take all the possible values. In this case, the example is that there's 4 different values for weather. It can be sunny, rainy, cloudy, and snow. And then you have per value, per event, you have the probability given. And if you have a probability space, then it should sum up to 1, so that you have the complete set of all the possible assignments written down as a probability distribution. Then the next notion that you should be all familiar with then is a conditional probability, that if you have a certain event, what is the probability that given a certain event, another event happens? So what is the probability of A happening under the assumption that B has happened? And that is defined as the probability of the two things happening together divided by the probability of the other one happening. Or in an alternative form, that's a simple rewrite, is just to write the probability of two things happening at the same time as the conditional probability times the probability of the event B. So that's twice the same thing, just written in a different way. It's this product rule that's often used in practical applications that you need to apply it. So slightly more examples, so that now if we look at our example, cavity and toothache, because that's the one we use as an excuse to start with this probability theory, you can now represent, given that someone has a toothache, what is the probability of this person having a cavita? You can represent this now with the probability. Given that toothache is all we know, we don't need any more information, we don't have more information. But if we know, for example, that this person has a cavity, then the conditional probability will be 1 in this case. And in some cases, if it's an independent information, then the fact, for example, that If it's sunny outside, the weather, one more value, it might give you the same conditional probability if these two events are independent. Different, just some examples of using this. What is interesting now is if we have more of those variables and we want to combine them in some way, we can do this by defining joint probability distributions, and they are basically systematically enumerating all the different options. So if we have here two variables with 4 values and 2 values, then we can do this by a 4 times 2 matrix and just say that we have a probability of a cavity being true while it is sunny and so forth, and we can just enumerate all the probabilities for the possible combination of values. And this allows us then to do inference, because if we have this joint probability distributions, we can in principle answer all the questions over the probabilities that we need. So here's an example from a slightly more worked out. So this is apparently an instrument from a dentist. It's a catch or not a catch. And this is the representation of a joint probability distribution of three events with 2 possible values, namely cavity or not cavity, catch or not catch, and toothache and not toothache. So we have 2 times 2 times 2 possible combinations, and they are represented in these 8 fields. So the proposition then of the value of a proposition is just the sum of over all the different atomic events. So if we have, for example, a proposition that we want to show that someone, the probability of someone having toothache, we just have to add all the probabilities of this joint probability distribution where the toothache is true. So this would give us a probability of 0.2. But we can also do this for conditional probabilities. That, for example, the probability that someone not having a cavity, given that he has toothache, is then related to this only the toothache part of the joint probability. And you just calculate the not having a cavity and toothache part, which is this plus this, divided by the full toothache part, just by definition of the joint, just by definition of the conditional probability, and that gives you then the probability for this conditional probability not having a cavity or the toothache. So these were notions that I think you have seen, so I hope that wasn't too fast or too slow, whatever. One thing where this is really useful for is when you want to express the probability of a cause given some consequence. And this is what Bayes' theory helps us to do, that if we know the probability of a consequence given a cause, then we can inverse this using a simple mathematical theorem, and that's very useful. That's also one of the few things about this that you really should be able to do in the exam, to calculate with Bayes' theorem some expectation of given some consequence, what is the cause? So some diagnosis of a problem. So here is the Bayes rule. I guess this is also part of the course, so you're aware of that. And that's just the conditional probability of A happening under the assumption that B can be calculated the other way around. So here you have the probability of B happening if A happens, multiplied by the probability of A happening itself, divided by the probability of B. This is sort of the famous, one of the ultimate rules in probability theory. It follows very, very trivially from the knowledge we have about probabilities. So there's a simple proof that this rule is true, but it turns out to be very handy anyway. So the proof is that, so we take the right-hand side. This is the right-hand side of the the theorem, we take the definition of conditional probability B under the assumption that A has happened, which is this bit. So the conditional probability B over A is that B and A happen at the same time, divided by the probability of A happening. Then we can get rid of the P of A, which gives us the probability of B and A happening at the same time, divided by P of B. And that gives us, again, the conditional probability A under the assumption that B happens. So it's a very simple proof that these two things are the same, but it's very useful anyway. Yeah? And the example that to which you want to use this is that you're interested to predict whether someone has a disease, given that there is some symptom that you can measure or that you can see. But typically it's the other way around, what you know is that you have pneumonia, then you will cough. But you don't really know how often people who cough have pneumonia. So this is information that's far more difficult to get to. And very often this test results, what do they really tell you under the assumption that someone has a disease, as opposed to does someone has a disease when there comes a certain test result. And also, which we will see on Monday, then how can you use this for spam prediction? Because we know we know more often that if there is given use of words, then we know whether it's spam or not. That's easy. But for all the spams, what are all the words is sometimes more difficult to estimate. So here is the example of the usage of Bayes' rule. So you have a tumor with a prior probability, so it's very unlikely to happen, so it's only 1% that it is malign. And then you test the radiological test to determine what its nature is, and the probability that this malign tumor M yields a positive test result is 0.79%. 79%, which means that there is a relatively high false negative rate. And the probability of the negative result for a benign tumor is relatively high, with a smaller false positive rate. Then if you get this information and you give it to a doctor, then the experiments show that they estimate that the patient really has the malign tumor is heavily overestimated. And you can, in principle, simply calculate this via the Bayes rule, how much it is. So you take the probability of, given the test result, that it is a positive result, times the probability of it happening in the first place, and then you have to normalize it according to the fact that whether the test is positive or not. And the result of this shows that it's really the doctors are off just by misunderstanding the probability theory by an order of magnitude. So the fact that you really, the probability that you have the disease is often smaller than one would expect if you don't do this, if you don't calculate this properly. But I guess this is examples that you have seen in the course, so that's it was probably better explained than how I explained it here. So this is an interesting thing anyway, and it shows you how useful it is to really formalize these kind of expectations and probabilities, because it's very, very difficult to rely on your intuition here. What are the dependencies and what is the impact of some things being more frequent or more probable and so forth. So there are two things I think that makes it difficult. The one thing is that for the probabilities, we need a lot of data to estimate the prior probabilities. And if you also think, but that's something I will talk about in a minute, that if you take the full joint probability distribution, you always need the full combination of all the values of all the events. and that basically is an exponential blow up that you never can calculate fully. So here the problem is that we don't have enough ways to calculate the prior probabilities. And one way of dealing with these problems is to reduce to introduce the notion of conditional independence, and to make sure that you do not have to calculate the combinations of which you know a priori that they do not have impact, they don't impact each other. So if you have two events of which you know that they are not impacting each other, you don't have to integrate them in one joint probability distribution if you want to do your calculations. And that's where the idea of Bayesian networks come from. Is it also something that was covered in the course in statistics, or no? You shake your head, you don't remember? Okay, so maybe I sort of betted on the wrong horse. Maybe I should have spent more time on this. I just want to explain the general idea here, because basically what you see is that if your decision tables become too big in order to calculate the probabilities of some conditional probabilities, it is a good idea to split the events in dependencies and independencies. So if you have an independent event, you can simply treat them independently, also in your algorithmic approach. And the way that's done is that you split, in principle, for all the propositional variables, you have a node, and the nodes form an acyclic graph. And then you have the probability distribution is conditional on your parents in the graph. So then you get this kind of topology. If we have information about the weather and we have information about tooth problems, then we can, in most cases, we can say these are independent events. So we can simply treat the weather on the one hand with all its values, whether it's sunny or not. We can calculate the probabilities of if the weather is good, something else according to the weather happens, and we can treat the problem of the toothache independently. And here, as I said, the probability given some of the children is determined by the parents. So and in this case, basically, we assume that those two things are conditionally independent. And then basically, we only need to do the joint probability distribution between the parent and the children. And that obviously saves an enormous amount of complexity, because you don't have the full n by n by n by n data structure you have to take care of, but only the ones that are related in these dependencies. So if you here is an example from the book. And you can see that these guys, they work in San Francisco, I think they did, or in Los Angeles. So I think it was San Francisco. So it's they're very busy with dealing with earthquakes. It might not be the example I would have come up immediately, but so they're at work. Neighbor Jones calls to say the alarm is ringing, but the neighbor Mary doesn't ring, so doesn't call. So there are two chances: the burglar, or is it an earthquake? So we have 5 different variables. We have the event of a burglary, the event of an earthquake, the event of the alarm going off, the alarm of John calling, the event of Mary calling, and then we could have a very complex joint probability distribution to calculate all the things, but it might be better to organize this in a network structure. So we know that a burglar can set off the alarm, an earthquake can set off the alarm, and if the alarm bells rings, we have 2 possible events, namely Mary calls and John calls. Yeah, that gives me then this network structure. So burglary is an independent event. We don't have any knowledge about when it happens, why it happens, and so forth. And the probability can be defined as a prior, so 0.1 or whatever, and the probability of an earthquake can also be specified from experience as a prior. And then the question of whether an alarm rings, we know that we have 2 events that can cause this, so it's dependent, it's a conditionally dependent event from the 2 possibilities of B or an E. And if B is true and E is true, then 95% of chance that my alarm goes off. So if there is both a burglary and an earthquake, then my alarm should go off, unless it's really broken. If there is a burglary, it goes off. It's an earthquake. It also sometimes gets off, but not so often. And if neither of them, there is a very small probability that it goes off just by mistake. So that would be an error in the system. So this is now the full information we have about the alarm, the full probability distribution, which is sufficient because we have based this on the fact whether it's a burglary or whether it's an earthquake, because these are the only events that can cause the alarm going off. And then, again, we have the John calls thing, which is independent from the Mary's call thing, because they don't know each other, they may, probably, in this example. And I know that if the alarm rings, then 90% John will call, because he's sort of a very reliable person who's always at home. Whereas Mary, she's often at work and she doesn't notice that there is an alarm, so she will ring with the slightly less probability. And this is a sort of a way of representing the knowledge that you need, so that we can now reason and argue over these probabilities without having to represent the full joint for the probability distribution. And that's basically all I wanted to say. So Bayesian networks is a very active field of research, because it's a good way to model the probability of events that are in complex environments that might be dependent or independent, and it helps you to sort of tame the complexity of the probabilistic reasoning that otherwise would be very problematic. Yeah? So the good thing about probability is that it has a sound theoretical basis, it's mathematically well developed, and it's very useful for decision making. We will see a bit of decision making next week for the classification problem. We don't make any use in our Schnapsen game, because first of all, I'm not an expert here, so maybe there is a better use to what we do, but I think that the probabilities of the different hands happening is the same for all the different hands. So if we have unknown cards and we assume that there are different belief sets, the probability of each of these belief sets to happen is the same. Because there's so there is no way of really reasoning over one situation is more probable than another. That's different to the case of backgammon that we had in one of the first lectures, or where you know that a 1-1 is very, very rare to happen, so you don't need to really take care of the event happening that you get a dice that gives you the value 2. So the likelihood, the probability of this event happening in backgammon is so much lower that you should take care of this, and you should take it into account in your decision-making process in your game algorithms. So here that would make sense. In our case, to the best of my knowledge, it doesn't really make sense to apply a probabilistic approach, apart from using it maybe for classification, but we might use other algorithms for that later next week. So there are good tools for it. There are very good implementations also for Bayesian networks. So it's I think a very well established theory. And I mean, you have followed a course on how to apply this in experimentation. So this is, I think, something really important particularly for the EMM students and the LE students who are more in these sort of experimental spaces. So I think it's a very important toolkit to really be fluently in and to be able to work with. For us, for the exam, I really would like you to understand how to apply the Bayesian rule in some practical example and the basic notions, and in principle that's good enough for us here. It's computationally problematic. It's not always easy to calculate all the probabilities. You need often much data to calculate the priors. Sometimes difficult to get to the prize in the first place. Yeah, so what I said in the beginning, the interpretation of this is not trivial. So even if we get something back that's mathematically well-founded, so the probability of someone cheating on his wife is 20%. What it really means is not so easy, and we see that often enough that people really completely misinterpret statistical information in the newspaper articles and so forth. So you have to be really careful before you apply, you make statements about probabilities, that you really understand what they are all about. So there is little time, but enough time to briefly talk about exam and final project. I don't want to spend too much time again on it, but it's good sort of reminding ourselves what I mentioned in the beginning. Maybe before we get into this, is there any other questions that I should now take care of, or anything? Nope. Okay, so let me briefly talk about the exam. So in principle, what you should be able to do is everything that you've done in the working groups with Denise or Dalia, or me or Finn this morning. That includes informed search, uninformed search with hill climbing best fit search and A star. I haven't mentioned beam search, so I will take that off. There is a list on the Canvas page that I will update again, but it's that contains the learning objectives of the course, and that is basically this kind of list, but it needs a little bit of updating to, for example, here it says beam search, which I should have taken out. The old list might still say resolution calculus, which I only want you to understand the basic idea, but not necessarily apply it in class as we have in the exercises. So there is a list of topics that you should be able to apply things and to answer the basic questions that I've been discussing here in class. So you should be able to reproduce things and calculate things, apply the technique. So basically the idea is some indicative that I want to give 25% of the points to the lecture stuff. So go through the slides, things that I have said in the slides, not sort of the minor detail on slide 75 on the bottom left-hand corner, but sort of the general idea, the definition of what is soundness, what is entailment, what is an event space, these kind of basic notions. I really want, you just have to learn them, sort of stomper, as it does say. More important is that about half of them will be do questions, so you get some simple questions, fill in a truth table with the possible values, apply Bayesian rules to predict some consequences and so forth, and some explain and reflect questions. So you might have to, in open questions, type something in the system. And it will be a digital exam, but I'm turning a little bit more back to open questions where you just have to type in the answers and we look it up. So it takes a little bit more time checking it, but it's I think easier to really get valid questions. So I prepared the sort of the partial quiz last week for the questions of the first week. This should give an indication of how the exam will look like. So we'll have these kind of questions, but the one from last week, they were more or less what you had seen. So a third of the content, so you expect 3 times as much and this kind of complexity, and maybe a little bit more difficult. I will publish next week the practice exam, probably the exam from last week, from last year, and we'll discuss it in class, go through the questions so that you know what kind of questions to expect and what we expected last year, so that you can prepare for the exam. And then the final project, I said a little bit about it yesterday, still a tiny little bit more time because we have now 5 minutes left. So the project is about Schnapsen. In the exam, there is nothing really about Schnapsen. So if there is some exercise that uses Schnapsen as an example for motivation, so the rules will be clear that you should apply. So it's because we have people who don't have to do the practical. the main goal of the project is to understand the methods, as I said. So it's not about being a brilliant programmer. It's always nice if you're a brilliant programmer, but that's not what this course is about. It makes it easier if you have the techniques easily mastered. But the idea is really we want you to show that you are capable of understanding the impact of choices in the method on the tools that we build. So I really like the discussion we had in the break that we now have these knowledge-based agents. And what happens if you apply a machine learning algorithm on your humanly trained bot, intelligent agent? Will it become better than the one that just applies the human knowledge? Or will it be worse, or will it overfit? And the interesting thing is that the hypothesis I had in the beginning, and I think you also had it, is that it would be ideal if we take some human knowledge and then we play it against others, we train it on other tools, and that will improve the quality of the bot. But the experience with AlphaGo has shown that there is a new tool, AlphaZero, that does not take into account any a priori knowledge, and it outperforms the other one, the AlphaGo, the original one. It outperforms it. So the hypothesis that integrating knowledge in the learning process is incorrect. I think this is a really interesting question why this happens, and it's an interesting kind of research that we can perform next week on not Go but on Schnapsen. Exactly the same research question. This is the kind of things where you could find some niche. It's often really small research we can do here. But find a niche where you think, oh, that would be interesting to understand, and surprise us with interesting answers to these hypotheses and ways of approaching this. And obviously, it's all about generic conclusions. We're not so much interested in your specific application, your specific algorithm. But what does it say us about the relation between learning algorithms and knowledge, basic a priori knowledge? And then you have to write a scientific paper. So I think you have all followed courses like paper writing. I'm not always sort of 100% sure whether there are different ways of writing papers. Let's put it like this. And when in the peer reviewing, we sometimes get relatively harsh criticism on other papers on the style. So I think, for example, the idea in which way you address your audience. So can you write, we built a bot and? So I often hear that you're not allowed to use the term we or I in these papers. This is debatable. So because we are in engineering science, we built something, so it's very difficult to avoid this. What I think is the critical thing is that we never talk about processes of how we did the research, we only talk about the results of the research. So I do not want to know that someone wrote a bot on the Thursday night because the grandmother was ill, and obviously I'm now sort of exaggerating terribly, but sometimes you get these kind of things. So first we built a bot A, but then it turned out that it was outperformed by bot B. I do not care whether you did A first and B later. What is important is that you tell me that there are two bots, and one outperforms the other, and it's fine that you say, okay, we wrote 3 bots, and one performs the other. Fine, that's not the problem. But never tell me, when did you write it? Why did you write it? In a sort of personal way, yeah?
But the reason why I wrote this was first and that was second, it's like it shows the way of reasoning, how I think that this model should work, and what is the difference between expected result and the real result?
Yeah, but so the point was that this order reflects the way that you think about your bots. But I don't care how you think about your bots. I care about what these bots are and what they do. So it's a very subtle difference. But That's the sort of the challenge for you when you're writing the paper. I showed you the structure yesterday. The research procedure, I think, is important. Oh, I'm running out of time. Sorry. Probably there is no need to do it today. So let me postpone this because there are some more slides, and I think it's quite good to discuss this in a bit more detail. But you will not start writing the paper now anyway. But I think let me give you this one slide, and that is the research that you should do. Think of it in ways that you implement at least 4 bots or more. If it's 3 and they are really, really interesting, fine. But then you compare the performance. How do you compare the performance? We gave you the play script and the experiments and the tournament, but that doesn't give you automatically a measurement for which bot is better than the other. So come up with a systematic way of performing and comparing 2 intelligent agents. It wins more often, it wins more comprehensively, it wins more on 1,000 games, it wins more on 100,000 games, it wins faster. There are many different ways of defining quality of your performance of your bots. Then study the results. Which one outperforms better? Which one? But you have to set your measurement first. And then come up with some interesting hypotheses and verify them and falsify them. Ideally, show them with the statistical grounding. I've run 1,000 experiments and I get this kind of deviation. Is it statistically valid? Are my results statistically valid? And here you can apply the probability theory. And then you write the paper, and I will explain on Monday, or we'll talk about a bit more on how I would write this paper. But think about these 3 things in the beginning on how to set up your research. And then let's see on Monday. Apologies for running over time. Have a good weekend. Oh no, so tomorrow.